All right, this video is going to be the first video of the Waves Part 2 packet. So this is going to go over pages 4 through 7. So we're going to be talking about sound here. So sound is a wave, and by the properties of waves, it needs a source of energy, and it needs a medium to travel. Now, it could be material medium, which would be a mechanical wave. So that's like a rope, air, water. Okay, or it could be space. Space is still considered a medium. It's just a non-material medium. Okay, the source of energy of a sound wave, though, is going to be a vibration. Okay, so how we talk, okay, so like your vocal cord right here, is you basically press air out of your lungs, and what your vocal cord does is it constricts, releases, and it causes these vibrations in the air that make actual audible sounds, okay, that you pick up as words, things like that. Now, the medium a sound wave travels through is usually going to be air. Okay, that's what we usually deal with. But sound is also very good at traveling in liquids and solids. Okay, so air is actually the slowest. Okay, so the particles are very far apart, so it's very hard to transfer the energy to the next particle. Liquids is even better. Okay, so that's why you can hear better underwater. Okay, because those particles are right next to each other, so they can transfer energy better. And then solids are even better. You can transmit sound very well through solids because the particles are so close to each other. And if your goal is to hand off energy to the particle next to it, it helps if it's right there. Okay, so sound, since air is a material medium, sound is a mechanical wave, so meaning it needs a material medium. Okay, so sound displaces air particles parallel to the direction of the wave of the motion. So that means you have a particle that does this. It basically goes back and forth. Okay, it vibrates back and forth, but your wave is also moving in this side-to-side direction as well, the direction of it. So that's why it's parallel. So that would make it a longitudinal wave. Okay, so remember we talked about a longitudinal wave. The transverse wave was the other one. That is the one that does this. A sound wave is not a transverse wave. But we can also call it a compressional wave, where it just compresses back and forth. So compression wave. So since sound is a wave, it can be characterized by all the properties of waves, so velocity, frequency, wavelength, amplitude, so stuff we've already covered. Now, two of the properties of the sound waves are perceived by different sensations in humans. Okay, so frequency is responsible for pitch, okay, basically how high a sound sounds to you. Okay, humans can hear a range from about 20 to 20,000 hertz, so that is our audible range. Okay, now frequencies that are below 20, which is hard for us to hear, those are called infrasonic. Infra means below. Now, you could also say it's subsonic too. That's fine. Okay, but thing about though is elephants. Elephants actually can communicate at frequencies that are lower than 20 hertz. So it may look like they're doing nothing to you, but they could be communicating, and you wouldn't be able to hear it. Now, frequencies above the audible range are called ultrasonic. Now, you could say supersonic as well. That's fine. Both mean above, so ultra means above. Okay, so that would be something like a dog whistle. So dogs can hear very high frequencies, so that's why a dog whistle is very efficient for them, because they can pick up that sound, and it doesn't really affect us. Now, that was pitch. Now, amplitude is responsible for loudness. Okay, so that is when you turn your stereo up, what you're doing is you're adding energy to a wave by increasing the amplitude of that wave. Now, loudness is measured in decibels. Okay, dB for short. Okay, it's basically just the ratio of pressure of a given sound to the pressure of the softest sound we can hear. So 0 decibels would be the lowest you can go. Okay, now every 10 decibel increase represents a sound that is going to be 10 times louder. Okay, and we're going to do an example here in a second, is how much louder is 80 decibels over 40 decibels? Okay, so let's say we go 40 to 50 to 60 to 70 to 80. Okay, so from 40 to 50, that would be 10 times louder. Okay, now 40 to 60, okay, so 40 to 60, I'm going to kind of draw, so 40 to 50 would be 10. 40 to 60, every time you go up by 10, you're going to add another 0. So 40 to 50 is 10, 40 to 60 is going to be 100 times. Okay, now you go 40 to 70, we're going to see where they meet up. Okay, 40 to 70, it was 100 times. Now it's 1,000 times. And we keep going, 40 to 80. Okay, where they meet up, we're going to add another 0. and so that is 10,000 times louder. Okay, so you may not think going from 40 decibels to 80 decibels is that big a deal, okay, but it's actually 10,000 times louder than it was. Okay, and we'll do more practice on that here in just a second. Now, resonance, that is a term that kind of gets confusing for people. Okay, so every object has a natural frequency that it wants to vibrate at. Okay, or oscillate. Oscillate just means go back and forth. So this is the frequency of an object tends to vibrate when hit, struck, plucked, strummed, somehow disturbed. So like think like a guitar string. Okay, when you pluck a guitar string, that string has a natural frequency that it wants to vibrate at. Now, if the amplitudes of the vibrations are large enough, then we can actually hear those sounds. Now, resonance, though, is the increasing of amplitude, okay, due to the periodic force that is the same frequency as the natural frequency of vibration or oscillation. So what that basically means is you say you have a wave doing this, and say you have another wave that has the same amplitude, same frequency, okay, and what happens is when they meet each other, they're going to line up perfectly, and it's going to create an even bigger amplitude. Okay, so let's just say these lined up perfectly. So my new one, I'm even change colors. My new one, once they combine, is going to create this even bigger amplitude. Okay, so, and I'll talk about an example here in just a second. Now, energy is transferred every time the force is applied, and the interference is always constructive interference. So that's when you see the amplitude get even bigger. Okay, that would be constructive interference. Okay, so a good example of this is how a wine glass is broken. Okay, so a wine glass has a natural frequency that it wants to vibrate at. Now, some singers can actually achieve that same frequency of the glass. And what happens is once those waves line up perfectly, they make each other bigger, okay? And so it's going to create this higher amplitude, which higher amplitude means higher energy, and a glass can only take so much energy before it breaks, okay? Another example would be like basically how you tune an instrument, okay? If you've ever tuned an instrument, what people do is, especially if you use like something like a tuning fork, if you strum the string, like say I have a C string and you strum the C string and you tap a C tuning fork, you'll be able to hear their frequencies line up, and it almost sounds like this beating pattern, like this wah, wah, wah. So it lines up perfectly where it sounds louder than quieter, but it syncs up perfectly, and that's how you basically tune something is you're trying to match that frequency up to where you hear that higher amplitude. Okay, so that is what resonance is. Now, intensity, that's what we kind of just talked about was decibel level. Okay, so intensity is basically how loud something is. Okay, that deals with amplitude. And we talked about decibels. So it says decibel scale ratings are logarithmic. So that means it goes up by a factor of 10. Okay, so if you went from 0 to 10 decibels, well, that would be 10 times louder. Okay, if you went from 0 to 20, okay, that would not, so what I mean by going up by 10, it wouldn't be 20 times. That would be wrong. Okay, you have to go up by a factor of 10. So 10 times 10 is now be 100. My next one would be, what's 100 times 10? Well, now that's 1,000. Okay, so that's what it means by logarithmic. And we're going to do some examples here in just a second. So number one, it says, how many times louder is the sound of 60 decibels compared to 0 decibels? So I'm going to show you two ways to do this. I'm going to show you the long way and the short way. Okay, so let's do the long way. So if I go from 0 to 60, oh, we already messed that up here. 0 to 10, 10 to 20, then to 30, then to 40, then to 50, then to 60. Okay, so 0 to 10 would be 10 times louder. 0 to 20 is going to be 100 times louder. And I'm just doing this so when you look at this and you see my 100 times louder between 10 and 20, that's not me saying 10 to 20 is 100 times louder. That's me saying 0 to 20 is 100 times louder. Okay, so 10 to 20 would just be 10 times louder. Okay, so 0 to 30 is going to be 1,000 times louder. 0 to 40 is going to be 10,000 times louder. 0 to 50 is going to be 100,000 times louder. And then 0 to 60 is going to be 1,000,000 times louder. So that's a lot. Okay, if you go from 0 decibels, which is the minimum threshold of hearing, okay, you can go to 60 decibels, which is not that loud. Okay, it's actually 1,000,000 times louder than it was at 0. Okay, so that would be your answer, would be 1,000,000 times louder. Now, you could also do it this way is how many times did you go up by 10? Okay, I went up by 10 6 times. So you could also say, or it goes up by 10 to the 6th power, which is basically the same thing as saying 1 with 6 zeros behind it. So 1, 2, 3, 4, 5, 6. So that is the same thing as saying 1 million times louder. Okay, so either way, so however way you want to do that. Now, for like a number 2 problem, I would probably recommend that. I wouldn't do the 0 to 130, okay, because that's just going to, I mean, you can if you want to. That's just going to take a long time. If I go from 0 decibels to 130 decibels, you went up by 10 13 times. So that basically means you went up by 10 to the 13th power. So I'd be fine with that. Or you could even say 1 times 10 to the 13th. That just means that's 1 with 13 zeros behind it. So that just saves you time. Number 3 basically wants me to show you how is 80 decibels 100 times louder than 60 decibels. Okay, so 60 to 70, 70 to 80. So it starts off at 10 times, then it would be 100 times. You could still do the exponent way if you wanted to. If you go up by 10 2 times, that's the same thing as saying 10 to the 2, which is 10 squared is 100. So either way would be fine on that. Okay, so let's go here. So we're just going to talk about, I'm not really worried about testing on this stuff. This is just being careful with decibel exposure. Okay, so a loud stereo can be at 90 decimals. Okay, so if you put an earbud in your ear, okay, through your AirPods, it can get up to 110 decibels, and that's 110 decibels focused on your eardrum. Okay, now loud concerts can get up to 120, so you're like thinking, well, how can my headphones get that loud? They can get pretty dang loud, and you got to think about it's purely focused on your eardrum. Okay, at concerts and stuff, yes, it's hammering your eardrum and stuff, but those sound waves aren't directly focused on your eardrum. There's a lot of sound waves going off in different directions. Okay, but regardless I think the pain threshold is about 120 decibels. Okay, so damage can be temporary. Okay, so like if you ever left a concert and your ears sound like they're muffled, okay, that would be a temporary thing. Now, hopefully that's temporary. If your ears sound muffled all the time, that's probably a permanent thing. Okay, so like an example for mine is I've been telling my class is I've listened to a lot of music, I've gone to a lot of concerts, and I hear ringing in my ears when it's quiet and stuff, so that's actually called tinnitus. Okay, so once these cells, these little hair-like sensory cells in your ears are damaged, they're done. Okay, so that's what you got to be careful is if you're blaring your headphones, you need to be really careful on how long you're exposing them to and how loud it goes, because once that hearing goes, it's not coming back. Okay, so again, so what was the range of human hearing in hertz? It was 20 to 20,000 hertz. Okay, so again, that's how high we can hear. There's animals that can hear a lot higher than we can or a lot lower. Vampire bats can get up to 210,000 and dolphins can get up to 280,000. Okay, so, and that will end that one.